At this very moment, something is watching Earth from space, and it's been taking notes for 4.5 billion years. The moon has recorded every asteroid impact, every cosmic catastrophe, every moment of violence our planet somehow survived. But those records aren't just history lessons. They're warnings about what's still coming. The Chelyabinsk meteor that injured 1,500 people in 2013 was just a preview. The moon reveals a terrifying truth. Impacts aren't rare accidents. They're statistical certainties operating on timescales that dwarf human planning cycles. But here's the twist. The same craters documenting this ongoing threat contain blueprints for our survival. Hidden beneath that familiar gray surface lies water, oxygen, metals, and natural shelters that could support human civilization beyond Earth's vulnerable atmosphere. The moon isn't just our companion, it's our lifeboat. Stay until the end and discover how our nighttime guardian has been preparing humanity's insurance policy against a more dangerous cosmos than we ever imagined. The moon, Earth's missing archive. While Earth desperately tries to erase its own past, the moon keeps perfect records. Every raindrop that falls, every wind that blows, every living thing that grows, they're all conspirators in Earth's grand forgetting. Our planet is a master of reinvention, constantly recycling its surface, burying its secrets under layers of sediment and time. But 400,000 kilometers away, something else entirely is happening. The moon sits there like a cosmic freezer, preserving everything we've lost. No atmosphere means no weather. No weather means no erosion. No erosion means that every scar, every impact, every moment of violence from the past 4.5 billion years remains exactly where it happened. Think about that for a moment. While Earth has forgotten its first billion years completely, the moon remembers every single day. NASA's Lunar Atmosphere and Dust Environment Explorer mission confirmed what scientists suspected. The moon has virtually no atmosphere at all, just a whisper of helium, neon, and argon so thin it barely deserves the name exosphere, a few atoms per cubic centimeter. On Earth, you breathe about 25 million trillion molecules with every breath. On the moon, that same volume of space might contain a dozen particles drifting alone in the vacuum. This airless perfection makes the moon the most reliable archive in our solar system. When something hits the moon, it stays hit. The Gravity Recovery and Interior Laboratory mission, known as GRAIL, mapped the moon's gravity with extraordinary precision, revealing buried ring systems and basin structures that have been perfectly preserved beneath the surface for billions of years. These are the moon's deepest secrets, massive impact signatures invisible to the naked eye, but written in the language of gravitational anomalies. But here's where it gets interesting for those of us living on Earth right now. Those scars aren't just ancient history. They're a logbook of when large objects have been hurling themselves through the inner solar system. And according to recent analysis, something changed about 290 million years ago. The impact rate jumped, not doubled, jumped. The bombardment that had been steadily decreasing since the solar system's violent youth suddenly picked up again. Now this is where scientists start arguing with each other, which is always a good sign that we're onto something important. Some researchers see clear evidence of this late uptick in crater counts. Others question the dating methods or suggest we're reading too much into incomplete data. But here's what nobody disputes: impacts are still happening right now today. The moon's perfect memory tells us that large impacts aren't relics from the solar system's chaotic childhood. They're an ongoing feature of life in space. Every crater visible through a backyard telescope represents an object that could have hit Earth instead. Every ray system spreading out from impact sites like cracks in glass represents energies that would reshape continents. This isn't about dinosaur-killing asteroids. Those are vanishingly rare. This is about smaller objects, the kind that could devastate a region, knock out power grids, or create electromagnetic pulses that send our interconnected world back to the 19th century. Objects that explode in the atmosphere with the force of nuclear weapons. Objects that arrive without warning, traveling at cosmic speeds. Consider your smartphone for a moment. Consider the satellites that make it work, the power grid that charges it, the supply chains that built it. Consider how all of that complexity depends on a very thin shell of atmosphere and magnetic field protecting us from the violence of space. The moon's craters are receipts for violence that never stopped coming. But the moon isn't just keeping records, it's offering solutions. Hidden in permanent shadow at the lunar poles, water ice waits in quantities that could sustain human civilization beyond Earth. In equatorial pits where ancient lava tubes collapsed, temperatures hold steady at 17 degrees Celsius room temperature on an otherwise hostile world. In the regolith itself, oxygen and metals lie locked in every grain of soil, waiting for the right technology to set them free. The moon has been watching and waiting for 4.5 billion years, keeping perfect records of cosmic violence while offering everything we need to build a refuge from that same violence. It's a library and a lifeboat at the same time. But first we need to learn how to read what it's trying to tell us. What you're about to discover will change how you see that familiar face hanging in Earth's sky. The moon isn't the dead, boring rock we thought it was. It's a sophisticated early warning system, a natural fortress, and quite possibly the key to humanity's survival in a more dangerous cosmos than we ever imagined. The question isn't whether we need the moon's protection, it's whether we're smart enough to accept it. Civilization versus the cosmos. On February 15, 2013, the residents of Chelyabinsk, Russia discovered just how thin the line is between an ordinary morning and cosmic catastrophe. At 9:20 local time, a rock roughly 18 meters across slammed into Earth's atmosphere at 18 kilometers per second. The asteroid, about the size of a 6-story building, carried the kinetic energy of 440 kilotons of TNT. It exploded 23 kilometers above the city with a flash brighter than the sun. The shock wave that followed shattered windows across 6 cities, injured more than 1,500 people, and sent a reminder echoing around the world. Space is not empty, and Earth is not safe. Just 19 years earlier, astronomers had watched something far worse happen to Jupiter. Comet Shoemaker-Levy 9, fractured into 21 fragments by Jupiter's gravity, slammed into the gas giant like artillery shells fired by the cosmos itself. Each impact left scars the size of Earth-dark wounds in Jupiter's atmosphere that persisted for months. Jupiter, with 4 times Earth's diameter and 300 times its mass, absorbed impacts that would have sterilized our planet completely. These aren't stories from the ancient past. This is the reality of life in the inner solar system right now. Every day, about 100 tons of cosmic debris enters Earth's atmosphere. Most of it burns up harmlessly, the shooting stars you make wishes on. But sometimes something bigger gets through. The moon's crater-scarred surface tells us this has always been true. What looks like peaceful emptiness between the planets is actually a shooting gallery with Earth and the moon as targets. The difference is that Earth has weather oceans and plate tectonics constantly erasing the evidence. The moon keeps every receipt. Modern civilization has made us extraordinarily vulnerable to impacts in ways our ancestors never were. Our power grids stretch across continents. Our satellites form the backbone of global communications, and our food systems depend on just-in-time delivery networks that assume the lights will stay on and the trucks will keep running. An air burst like Chelyabinsk over a major city wouldn't just break windows. It could cascade through interconnected systems, turning a regional disaster into a global crisis. Consider what happens when the lights go out for more than a few days. Not just inconvenience, actual systems collapse. Water treatment plants fail. Hospitals lose power. Refrigerated medications spoil. Supply chains that deliver food to urban populations break down. Financial markets crash when electronic trading systems go dark. It's not the impact itself that kills modern civilization. It's the fragility we've built into every system we depend on. The moon's surface offers us a sobering catalog of what we're up against. Crater counts suggest that objects capable of creating regional devastation hit Earth roughly every few thousand years. City-killer asteroids arrive every few 100,000 years. Civilization enders are mercifully rare, perhaps once every few million years, but they are absolutely certain to come eventually. But here's where the story takes an interesting turn. For the first time in Earth's 4.5 billion year history, one of its species has developed the technology to see impacts coming and potentially do something about them. We've gone from helpless targets to active participants in planetary defense. In September 2022, NASA's Double Asteroid Redirection Test mission DART slammed into the asteroid Dimorphos at 6.14 kilometers per second. It was humanity's first attempt to deliberately change the trajectory of a celestial body, and it worked. The impact altered Dimorphos's orbital period by 33 minutes, proof that we can move worlds when we need to. This wasn't science fiction anymore. This was engineering, real spacecraft, real navigation, real physics applied to the ancient problem of rocks falling from the sky. The European Space Agency's Hera mission launching soon will examine the impact site in detail, teaching us exactly how effective kinetic deflection can be against different types of targets. But deflection only works if you see the threat coming. Most asteroids are dark, cold rocks that reflect less light than charcoal. They're nearly invisible until they're close, sometimes too close. NASA's Near-Earth Object Surveyor telescope launching in 2027 will scan space in infrared light, spotting the heat signatures of asteroids that optical telescopes miss entirely. The Moon plays a crucial role in this emerging defense network. Its gravity provides stable orbits for observation platforms. Its lack of atmosphere makes it an ideal location for sensitive telescopes. Its distance from Earth extends our warning time for incoming threats. Most importantly, its surface resources could support the industrial infrastructure needed to build deflection systems at scale. We're not talking about Hollywood scenarios where we nuke approaching asteroids at the last minute. Real planetary defense means finding threats decades before they arrive and nudging them into harmless trajectories with gentle, sustained pressure. It means building systems that work reliably for centuries, not just for one dramatic encounter. The Moon offers us something no spacecraft launched from Earth can provide: a permanent industrial base beyond our fragile atmosphere, with unlimited solar energy, abundant raw materials, and the gravitational leverage to send deflection missions anywhere in the solar system. It's not just a place to hide from cosmic impacts. It's the best possible location to prevent them. But first, we need to understand exactly what we're looking at when we stare up at those craters. Every ring, every peak, every terrace wall contains information about the forces that created it and the forces we'll need to defend against. The Moon isn't just keeping records of past violence. It's offering us a masterclass in cosmic survival written in a language of stone and shadow that we're only beginning to decode. Impact reality check. Look up at the Moon through binoculars tonight and you're staring directly at violence frozen in time. Every crater you can see, from the massive dark Maria to the smallest pockmarks scattered across the highlands, represents an impact that didn't hit Earth. Instead, the Moon is a cosmic dartboard that's been absorbing shots for 4.5 billion years, keeping a perfect score. But this isn't ancient history gathering dust in a cosmic museum. The Hubble Space Telescope's images of Jupiter after Shoemaker-Levy 9's impacts show us exactly what fresh violence looks like in our solar system. Dark scars the size of Earth visible from 600 million kilometers away, wounds that took months to heal in Jupiter's turbulent atmosphere. On the airless Moon, those scars would have lasted forever. The Chelyabinsk meteorite taught us something crucial about the nature of atmospheric impacts. The asteroid itself was relatively small, 18 to 20 meters across, about the size of a house, but it packed the energy of a small nuclear weapon. When it hit Earth's atmosphere at 18 kilometers per second, it didn't slowly burn up like the tiny particles that create shooting stars. It exploded. At 23 kilometers altitude, the rock simply couldn't hold together against the enormous forces created by ramming through increasingly dense air at hypersonic speeds. The explosion released 440 kilotons of energy in a fraction of a second, creating a shock wave that rippled outward at the speed of sound. By the time that wave reached the ground, it had weakened considerably, but it was still powerful enough to shatter windows across hundreds of square kilometers and injure more than 1,500 people. This is the reality of impact effects that most people don't understand. Hollywood has trained us to expect massive explosions and crater formation, but most cosmic impacts don't reach the ground at all. They explode in the atmosphere, creating airbursts that can devastate large areas without leaving any crater behind. The shock wave does the damage: a wall of compressed air moving faster than anything Earth's weather can produce. The difference between an airburst and a ground impact comes down to size and composition. Smaller objects, or those made of loosely bound material, tend to fragment and explode in the atmosphere. Larger objects, or those made of solid metal or dense stone, can punch through the entire atmosphere and excavate craters. Both can be devastating, but in very different ways. A ground impact creates a crater and hurls molten debris across vast distances. The Chicxulub impact that ended the dinosaurs threw superheated rock completely around the planet, igniting global wildfires and filling the atmosphere with dust that blocked sunlight for months. But an airburst can flatten forests, level cities, and generate electromagnetic pulses that destroy electronic systems across continents, all without leaving any permanent scar on the landscape. The Moon shows us the full spectrum of impact effects preserved in perfect detail. Small craters with simple bowl shapes record impacts by objects dozens of meters across the size range that creates regional destruction on Earth. Large craters with central peaks, terraced walls, and complex ring systems record impacts by objects kilometers across the civilization-threatening events that arrive every few million years. What makes the Moon such an invaluable teacher is that every impact signature is perfectly preserved. On Earth, crater counts become unreliable after a few 100 million years because weather and geological activity erase the older scars. The Moon has no such limitations. Every impact that ever happened is still there waiting to be cataloged and analyzed. Scientists use crater counts to estimate impact rates over time, combining thermal data from lunar missions with samples returned by Apollo astronauts to establish absolute ages for different regions of the lunar surface. The technique isn't perfect. Scientists argue about specific dates and rates, but the overall pattern is clear and disturbing. The bombardment never stopped. Recent analysis suggests the impact rate in the inner solar system increased significantly around 290 million years ago and remains elevated today. The evidence comes from crater counts on the Moon and other airless bodies, thermal evolution models of asteroid belt dynamics, and the discovery of impact debris in Earth's geological record. Not everyone agrees with this interpretation, but the possibility that we're living through a period of increased cosmic violence is too important to ignore. Here's what we know for certain. The DART mission proved that humanity can change the trajectory of an asteroid. On September 26, 2022, the DART spacecraft impacted Dimorphos, altering its orbital period by 33 minutes. This wasn't a gentle nudge. This was a 600-kilogram spacecraft hitting a 160-meter diameter asteroid at more than 6 kilometers per second. The impact created a debris plume visible from Earth-based telescopes and changed the asteroid's motion in exactly the way mission planners predicted. For the first time in the history of life on Earth, one species had deliberately moved a celestial body. Not by accident, not as a side effect of some other activity, but as a proof of concept demonstration that planetary defense is possible with existing technology. The European Space Agency's Hera mission will arrive at Dimorphos in 2026 to study the impact site in detail, measuring the crater dimensions and debris distribution to refine our models of kinetic deflection effectiveness. But deflection is only half the equation. The other half is detection. And that's where our current capabilities show dangerous gaps. Most asteroids are dark, cold objects that reflect very little sunlight. They're effectively invisible until they get close enough for their motion against the stellar background to become apparent. Sometimes that's not nearly close enough. NASA's Near-Earth Object Surveyor will change this when it launches in 2027. Unlike ground-based optical telescopes that hunt for asteroids by their reflected light, NEO Surveyor will detect their thermal signatures in infrared wavelengths. Every object in the solar system glows with heat, and that glow is visible to properly designed instruments regardless of how dark the object's surface might be or where it appears relative to the sun. The Automated Telescope for Asteroid and Tsunami Survey ATLAS already demonstrates the potential of dedicated detection networks. Operating from 4 sites around the globe, ATLAS scans the entire accessible sky every 24 hours looking for anything that moves. It has discovered dozens of small asteroids just hours before they hit Earth's atmosphere, providing real-time confirmation that the cosmic shooting gallery remains active. This is the new reality of life in the 21st century. We live in a solar system where impacts happen regularly. We have the technology to see most of them coming, and we're developing the capability to do something about the dangerous ones. The Moon's crater record tells us that impacts are a normal part of solar system physics. Our response to that reality will determine whether human civilization joins the long list of extinct species or becomes the first to actively participate in planetary defense. The question isn't whether another Chelyabinsk or Tunguska event will happen. It's when and where and whether we'll be ready. The Moon has been keeping score for 4.5 billion years. Now it's our turn to play. Reading the lunar surface. Stand in a field on a clear night and look up at the full moon. What you're seeing is a library written in stone and shadow, a reference work compiled over 4.5 billion years of cosmic archaeology. Every crater, every mountain range, every dark plain tells a specific story about the violence that created it. But first you need to learn the language. The most basic skill in lunar literacy is recognizing the difference between simple and complex craters. It's all about size, and size is all about energy. When a small object hits the moon, something in the range of tens to hundreds of meters across, it excavates a simple crater. These are the classic bowl-shaped depressions that look exactly like what you'd expect from dropping a rock into sand. They have smooth sloping walls, maximum depths about 1/5 to 1/7 of their diameter, and floors filled with shattered debris called breccia. But when something larger hits something a kilometer or more across, carrying the energy of millions of nuclear weapons, the moon's surface can't handle the stress. The initial cavity formed by the impact is so large and deep that its walls immediately collapse under their own weight. This is where crater formation gets interesting. In a complex crater, the unstable walls slump inward, creating terraced steps that look like an enormous amphitheater carved from solid rock. But that's not the most dramatic feature. At the center of the crater, the floor itself rebounds upward, forming a central peak that rises hundreds or thousands of meters above the surrounding terrain. This peak formation happens in seconds. Solid rock behaving like a liquid under the extreme forces of impact, then freezing instantly in its new configuration. The physics of central peak formation reveals something profound about the nature of matter under stress. During the impact, pressures exceed anything found naturally on Earth's surface. Rock doesn't just break, it flows like water, following the same rebound dynamics you see when dropping a stone into a pond. The central peak is literally a splash of rock frozen at the moment of maximum rebound. These morphological rules give you a cosmic ruler for measuring impact energies. A simple crater tells you the impactor was relatively small and fast. A complex crater with a prominent central peak tells you something much larger was involved, an object capable of regional or global devastation if it had hit Earth instead. Multi-ring basins like Mare Orientale reveal impacts so massive they sent shockwaves completely around the moon, creating ripple patterns in the solid crust that persist to this day. But crater morphology tells you more than just impact size. The depth-to-diameter ratio reveals information about the target material and the angle of impact. Craters in the lunar highlands tend to be deeper and more sharply defined because they formed in solid rock. Craters in the Maria, the dark volcanic plains, are often shallower because the impactors hit softer, more easily displaced basalt flows. Recent research has revealed something extraordinary about impact effects on the far side of the moon. High-resolution imagery from the Lunar Reconnaissance Orbiter shows canyon-scale valleys that appear to have been carved in minutes by debris flows from massive impacts. These aren't gradual erosion features like Earth's river canyons. These are scars carved by superheated ejecta moving at hypersonic speeds, gouging channels kilometers wide and hundreds of meters deep in the time it takes you to brew a cup of coffee. The implications are staggering. On Earth, we think of canyons as features that require millions of years to form through patient water erosion. On the moon, similar topography can be created in minutes by impact-driven processes. Its geology operating in fast-forward, demonstrating forces so extreme they reshape continents in seconds. This is why the moon serves as such a valuable laboratory for understanding impact processes. Every feature is preserved exactly as it formed, with no weather or tectonic activity to modify the original signatures. When you look at Tycho crater through a telescope, you're seeing the immediate aftermath of an impact that happened only about 100 million years ago yesterday in geological terms. The bright rays of material extending from Tycho across hundreds of kilometers of lunar surface are streams of molten rock and debris hurled out by the impact. On Earth, those rays would have been erased by the first rainfall. On the moon, they remain as sharp and clear as they were the day they formed, creating the spectacular ray systems visible through any decent telescope. Learning to read these features transforms lunar observation from passive stargazing into active investigation. That central peak in the crater you're observing, it's a natural laboratory containing rock samples from deep beneath the lunar surface, excavated by the impact and now exposed for study. Those terraced walls, they're cross-sections through the moon's crust, revealing the layered structure built up over billions of years of bombardment and volcanism. The moon's gravity field adds another layer to this geological story. The Gravity Recovery and Interior Laboratory mission created the most detailed gravity map of any planetary body, revealing mass concentrations or mascons buried beneath many of the large impact basins. These gravity anomalies mark places where dense impact melts settled to the bottom of crater floors, creating hidden mass concentrations that affect spacecraft orbits and reveal the three-dimensional structure of major impacts. For future lunar missions, this detailed understanding of crater formation becomes a matter of practical engineering. Smooth crater floors offer stable landing sites and construction platforms. Terraced walls provide natural ramps for accessing crater rims. Central peaks contain samples from deep crustal layers normally inaccessible from the surface. Even the orientation of crater walls affects thermal environments, solar panel efficiency, and communication line of sight to Earth. But perhaps most importantly, learning to read lunar craters teaches us to recognize the same signatures when they appear on Earth, or when we detect them around other stars. The Moon is our Rosetta Stone for understanding impact processes throughout the solar system and beyond. Every crater contains a story, every peak preserves evidence, and every ray system marks a moment when cosmic violence was transformed into a permanent record. The Moon doesn't just remember what happened to it, it teaches us how to recognize what's happening to us. Shelter in the gray caves, temperate pits. Hidden beneath the Moon's crater-scarred surface lies something that seems almost impossible, places where humans could walk around in ordinary clothes at a comfortable room temperature, naturally shielded from radiation and meteorites. After 50 years of thinking about lunar bases as high-tech pressure cookers requiring massive life support systems, we've discovered that the Moon has already built us perfectly good basements. The key discovery came from thermal measurements of mysterious pits near the lunar equator. These circular openings in the surface, some as wide as football stadiums, maintain a steady temperature of about 17 degrees Celsius. That's 63 degrees Fahrenheit room temperature all day, all night, through the 2-week lunar day when surface temperatures soar to 120 degrees Celsius, and through the 2-week lunar night when they plummet to negative 170 degrees Celsius. This thermal stability isn't magic, it's physics. These pits appear to be skylights into ancient lava tubes, natural tunnels formed billions of years ago when flowing lava carved channels through the Moon's crust. When the volcanic activity ceased, these channels were left as hollow tubes, some potentially extending for hundreds of kilometers underground. The rock overhead acts as perfect insulation, maintaining the temperature of the lunar subsurface, which never varies because there's no atmosphere to drive temperature changes. Japan's Kaguya spacecraft first spotted these features, identifying a skylight at Marius Hills that's approximately 65 meters wide and 80 to 88 meters deep. Ground-penetrating radar suggests the cavity extends horizontally into a much larger tube system, possibly a ready-made underground highway system stretching across significant portions of the lunar near side. For human missions, these natural shelters solve multiple problems simultaneously. Surface temperatures on the Moon swing across almost 300 degrees Celsius between day and night. Electronic systems struggle to operate efficiently across such extreme temperature ranges, and keeping humans comfortable requires enormous amounts of energy for heating and cooling. But inside a lava tube, temperatures remain constant year-round without any energy expenditure whatsoever. Radiation shielding presents an even more critical advantage. On Earth, our atmosphere and magnetic field protect us from the constant shower of cosmic radiation and solar energetic particles. On the lunar surface, astronauts are exposed to approximately 1.3 millisieverts of radiation per day, several hundred times the exposure from a commercial airline flight. Over months or years, this exposure becomes a serious health risk. But just a few meters of rock overhead reduces radiation exposure to Earth normal levels. The natural sealing of a lava tube provides exactly this kind of shielding without any construction effort. It's as if the Moon built us radiation shelters 4 billion years ago and has been maintaining them ever since. Micrometeorite protection comes as an added bonus. Earth's atmosphere burns up millions of tiny space particles every day, cosmic sand grains that would otherwise sandblast everything on the surface. The Moon has no such protection. Its surface is constantly peppered with micrometeorites traveling at several kilometers per second, gradually grinding down exposed materials and posing a hazard to both equipment and humans. Underground, this bombardment becomes irrelevant. What we don't yet know about these lava tubes is as intriguing as what we do know. How extensive are the tube networks? Are the ceilings structurally sound after billions of years of impacts and thermal cycling? How do you safely enter a tube whose ceiling might be unstable near the opening? These are engineering challenges, not fundamental obstacles, but they require careful investigation before humans start rappelling into 100-meter deep pits on the Moon. Robotic scouts will likely be our first underground lunar explorers. Lightweight rovers equipped with cameras, lights, and sensors could map tube interiors, test sealing stability, and identify the best locations for permanent installations. The same thermal stability that makes these caves attractive for human habitation also makes them ideal for sensitive scientific instruments that need to operate at constant temperatures. Some researchers speculate that lava tubes might contain more than just stable temperatures and radiation shielding. In the permanently shadowed portions of deep tubes, water, ice, or other volatiles might have accumulated over geological timescales. This is still speculation, interesting speculation, but speculation nonetheless, because no mission has yet ventured into the depths of a lunar lava tube with instruments capable of detecting such deposits. The construction advantages of building in lunar lava tubes extend far beyond environmental protection. Instead of landing construction materials on the surface and building structures from scratch, human missions could furnish existing spaces with relatively lightweight equipment. Inflatable habitation modules could be deployed inside caves, providing pressurized living spaces while relying on natural rock walls for structural support. Power systems could be simplified by taking advantage of constant temperatures. Solar panels or nuclear power systems wouldn't need to cope with extreme thermal cycling. Communication equipment could be protected from temperature extremes and micrometeorite damage while remaining accessible to surface antennas through the skylight openings. Even waste heat management becomes easier in a thermally stable environment. On the lunar surface, getting rid of excess heat is a major engineering challenge because there's no atmosphere to carry heat away through convection. Everything must radiate heat directly to space, requiring large, complex radiator systems. Underground natural rock mass can absorb and distribute waste heat more efficiently. The psychological benefits of underground lunar habitats might be as important as the physical ones. Instead of living in cramped, windowless containers on a hostile surface, lunar residents could inhabit spacious caverns with room to move around, areas for recreation and privacy, and natural acoustic properties that might make the space feel less claustrophobic than typical spacecraft interiors. Looking up through a skylight at Earth hanging in the lunar sky could provide a powerful psychological connection to home, a natural window in humanity's first permanent residence beyond Earth. These wouldn't be bunkers where people hide from the cosmos. They would be homes where people live comfortably while remaining connected to the larger universe around them. The moon has been preparing these spaces for us longer than life has existed on Earth. Now we just need to accept the invitation and move in. Rock ice and airless oceans of resources. Everything humans need to survive already exists on the moon. It's just locked up in forms we're only beginning to understand how to extract. After half a century of thinking about lunar missions as expensive camping trips requiring everything to be shipped from Earth, we're discovering that the moon is actually a hardware store, gas station, and water treatment plant wrapped in one convenient gravity-light package. The water story begins in the most unlikely place, the permanently shadowed regions at the lunar poles. These are areas that haven't seen direct sunlight for billions of years, maintaining temperatures below -200 degrees Celsius. In these cosmic deep freezes, water ice accumulates and stays frozen indefinitely. NASA's Moon Mineralogy Mapper aboard India's Chandrayaan-1 mission first detected surface-exposed water ice in some of these shadowed craters, providing direct spectroscopic confirmation of what scientists had suspected for decades. The Lunar Crater Observation and Sensing Satellite mission provided even more dramatic proof in 2009. L-Cross deliberately crashed into Cabeus crater near the lunar South Pole, and the debris plume it created contained clear signatures of water vapor, hydrogen gas, and even more exotic compounds like ammonia and carbon monoxide. The impact threw up about 6,000 kilograms of water, roughly the amount in a small swimming pool, from just a small crater excavated by a spacecraft the size of a car. Neutron spectrometers on the Lunar Reconnaissance Orbiter have mapped hydrogen-rich soils across the polar regions, strengthening the evidence for widespread water ice deposits. The distribution is patchy. Some areas show strong hydrogen signatures, while nearby regions show almost none. But the overall picture suggests substantial water resources waiting to be tapped by future missions. This isn't just interesting science, it's the foundation of a space economy. Water is everything in space. Split it with electricity, and you get hydrogen and oxygen rocket fuel and breathing gas. Keep it liquid and you have radiation shielding coolant for nuclear reactors, and the most essential requirement for human life. Every kilogram of water you don't have to ship from Earth saves approximately $50,000 in launch costs with current technology. But water is just the beginning of lunar resource extraction possibilities. Every grain of lunar soil contains oxygen locked up in mineral form. Ilmenite, one of the most common minerals in lunar basalts, is nearly 37% oxygen by mass. Silicate minerals that make up most of the lunar crust contain even more oxygen. NASA has already demonstrated oxygen extraction from simulated lunar regolith in laboratory vacuum chambers, proving that we can literally breathe the moon's dirt once we process it properly. The same extraction processes that liberate oxygen from lunar minerals also produce useful metals as byproducts. Iron, aluminum, titanium, magnesium, all the materials needed for construction and manufacturing are present in lunar soils in concentrations that would be considered ore grade on Earth. The only difference is the extraction methods, which need to work in a vacuum at temperature extremes. Molten regolith electrolysis represents one of the most promising approaches to lunar resource utilization. Heat lunar soil to melting temperatures in a vacuum furnace, apply electrical current and oxygen bubbles out of the molten rock while metals accumulate at the electrodes. It's essentially large-scale aluminum smelting adapted for lunar conditions, producing both breathable air and structural materials from the same raw material. The energy requirements for these processes are substantial but not prohibitive, especially considering that some near-polar locations receive nearly continuous sunlight. These regions, known informally as peaks of eternal light, experience sunlight for more than 90% of each lunar year. They're not truly eternal. The moon's complex rotation and orbital mechanics create occasional shadow periods, but they receive far more consistent solar illumination than any location on Earth. Solar panel arrays on these peaks could generate continuous power for resource extraction operations, with battery backup systems handling the brief shadow periods. The combination of nearby ice deposits and abundant solar energy creates natural industrial zones where lunar manufacturing could operate continuously with minimal imported equipment. The logistics of lunar resource utilization present interesting engineering challenges. Ice deposits are concentrated in permanently shadowed regions where temperatures never rise above -150 degrees Celsius. Solar energy is most abundant on sunlit peaks where temperatures can exceed 100 degrees Celsius. Moving materials between these environments requires either robust transportation systems or clever approaches to remote operations. One solution involves beamed power systems that can transmit energy from solar farms on sunlit peaks to mining operations in shadowed craters. Another approach uses rovers or pipeline systems to transport extracted materials from mining sites to processing facilities in more favorable thermal environments. Both strategies are technically feasible with existing technology, though they require careful system integration and redundancy planning. The environmental impact of lunar resource extraction deserves careful consideration. Even on an airless world, dust kicked up by mining operations spreads far in the moon's low gravity and airless environment, potentially contaminating scientific sites or interfering with astronomical observations. Responsible development requires understanding dust dispersion patterns and planning extraction sites to minimize contamination of environmentally sensitive areas. International cooperation on lunar resource utilization could set important precedents for space development beyond the Earth-Moon system. The Artemis Accords, signed by more than 20 countries, establish principles for peaceful lunar exploration and resource extraction, including transparency in operations and protection of historic sites. These agreements provide a framework for developing lunar resources in ways that benefit all nations, rather than creating new sources of conflict. The moon's resource potential extends beyond immediate human needs to enable further space exploration. Hydrogen extracted from lunar ice could fuel missions to Mars and the asteroid belt. Oxygen could supply life support systems for space stations throughout the inner solar system. Metals refined from lunar ores could build spacecraft and habitats without requiring materials to be lifted from Earth's deep gravity well. This transformation from resource scarcity to resource abundance could fundamentally change the economics of space exploration. Instead of every mission being a carefully rationed expedition carrying just enough supplies to accomplish specific goals, lunar-based operations could support open-ended exploration and development throughout the solar system. The moon has been sitting there for 4 billion years, patiently accumulating everything we need to become a spacefaring civilization. Now we just need to learn how to ask politely for what it's willing to share. Building on dust habitats, shielding. Living on the moon means learning to build with materials that want to kill you. Lunar regolith. The powdered rock that covers the entire surface is simultaneously the moon's greatest construction resource and its most persistent hazard. It's the foundation for every structure humans will ever build beyond Earth. And it's also sharp enough to slice through spacecraft seals, toxic enough to damage lungs, and clingy enough to coat everything it touches with a layer of abrasive dust that never settles. The radiation environment on the lunar surface makes this construction challenge even more urgent. China's Chang'e 4 mission measured radiation doses of approximately 1.3 millisieverts per day on the moon's surface, several hundred times higher than a commercial airline flight and about as much radiation as you'd receive from a chest CT scan every single day. Over months or years, this exposure creates serious health risks that no amount of personal protective equipment can address. The solution is elegantly simple: bury everything important under 2 to 3 meters of the same regolith that creates the dust problem in the first place. This much material provides effective shielding against both galactic cosmic rays and solar energetic particle events, while also stopping micrometeorites that constantly pepper the lunar surface. It's cosmic armor made from cosmic debris. But building radiation shelters from regolith requires solving the dust contamination problem first. Every grain of lunar soil has been fractured and refractured by billions of years of micrometeorite bombardment, creating particles with razor-sharp edges and electrostatic charges that make them cling to everything they touch. Apollo astronauts reported that lunar dust infiltrated sealed containers, coated optical surfaces, and even worked its way through multiple layers of protective clothing. The engineering solution involves what aerospace engineers call suit ports airlocks, designed so that spacesuits never enter the pressurized living area. Instead, astronauts climb into suits that remain permanently mounted to the outside of the habitat, do their surface work, then climb back out without bringing contaminated suits inside. It's like having a permanent clean room that dust can never enter. Electrostatic cleaning systems offer another approach to dust control. Since lunar dust particles acquire electrical charges from solar wind and photoelectric effects, they can be repelled using properly designed electromagnetic fields. Several research teams are developing dust mitigation technologies that could brush particles away from critical surfaces or prevent them from settling in the first place. The thermal environment presents equally challenging design constraints. Lunar surface temperatures swing from plus 120 degrees Celsius in direct sunlight to negative 170 degrees Celsius in permanent shade, a temperature range that exceeds the operational limits of most materials. Habitat designs must either avoid this thermal cycling entirely or incorporate materials and systems robust enough to survive repeated expansion and contraction. Underground construction offers the most straightforward solution to both radiation and thermal problems. Natural lava tubes provide ready-made spaces with stable temperatures and radiation shielding, but surface habitats can achieve similar protection using bermed construction techniques. Pile 2 meters of regolith over and around inflatable habitat modules, and you create Earth-normal radiation environments with excellent thermal mass to moderate temperature swings. The construction process itself takes advantage of lunar conditions in unexpected ways. In the moon's 1/6 gravity, moving large amounts of regolith requires far less energy than similar Earth-moving operations. A bulldozer that can push 10 tons of material on Earth can move 60 tons of lunar regolith with the same engine power. Construction equipment designed for lunar operations can be surprisingly lightweight while still accomplishing massive earthworks projects. Three-dimensional printing technology adapted for lunar regolith offers revolutionary construction possibilities. Heat lunar soil to melting temperatures about 1,600 degrees Celsius, and it fuses into a glass-like material stronger than concrete. Layer-by-layer deposition could build complex structures directly from local materials, creating habitats, landing pads, and roads without requiring any imported construction materials. Metal extraction from lunar regolith provides structural materials for applications where fused regolith isn't suitable. Iron, aluminum, and titanium are all present in lunar soils in concentrations that make extraction economically viable using adapted terrestrial metallurgy techniques. The same molten regolith electrolysis systems that produce oxygen for life support also generate useful metals as byproducts. Power systems for lunar habitats must cope with 14-day nights near the lunar equator, making energy storage a critical design requirement. Nuclear power systems offer the most reliable option for continuous operation, but they require careful integration with habitat shielding to prevent radiation exposure to inhabitants. Radioisotope thermoelectric generators like those used on Mars rovers could provide supplemental power with minimal maintenance requirements. Solar power systems designed for lunar conditions must be far more robust than their terrestrial counterparts. Micrometeorite bombardment gradually degrades solar panel surfaces. Thermal cycling stresses electrical connections, and the lack of atmosphere means cooling systems must radiate heat directly to space through large radiator arrays. But the payoff is substantial. Lunar solar installations receive unfiltered sunlight 24 hours a day for 2 weeks at a time. Life support systems built around lunar resources change the entire economics of long-duration missions. Instead of carefully recycling every breath of air and drop of water, lunar habitats could operate with much larger safety margins. Water extracted from polar ice provides not just drinking water, but also radiation shielding when stored in tanks around living areas. Oxygen produced from regolith allows for more generous atmosphere management and emergency reserves. Waste heat management becomes surprisingly challenging in the lunar environment. On Earth, we get rid of excess heat through convection and evaporation. Air carries heat away from hot surfaces and water evaporates to cool things down. Neither process works in the lunar vacuum. Everything must shed heat through direct radiation to space, requiring carefully designed radiator systems and thermal management strategies. The psychological aspects of lunar habitat design matter as much as the physical requirements. Earth is always visible from the lunar near side, providing a constant visual connection to home. Habitat designs that incorporate viewing areas or transparent sections could help maintain crew morale during long-duration missions. Underground habitats might include fiber optic systems to bring surface views and lighting into buried living areas. Emergency systems for lunar habitats must account for the basic fact that help is 3 days away at best and more likely weeks or months away. Redundancy becomes critical for all life-critical systems: backup power, backup life support, backup communications, and backup transportation to emergency shelters. The moon doesn't offer the option of walking to the nearest town when things go wrong. But perhaps the most important aspect of lunar construction is learning how to work with the moon rather than against it. The regolith that poses contamination challenges also provides unlimited construction material. The vacuum that complicates life support also enables industrial processes impossible on Earth. The radiation environment that threatens human health also preserves electronic systems from atmospheric corrosion. Building on the moon means accepting that we're not just visiting, we're moving in permanently. And our new home has already provided everything we need to build the infrastructure for the next phase of human expansion into the cosmos. We just need to learn how to use the tools it's been saving for us. Private space takes the hill. On February 22, 2024, something that hadn't happened in more than 50 years finally happened again. An American spacecraft touched down softly on the lunar surface. Intuitive Machines' Odysseus lander tipped over on landing and ended up resting at an angle against a rock, but it was still a functioning American presence on the moon for the first time since Apollo 17 in 1972. More importantly, Odysseus proved that private companies could deliver scientific payloads to the lunar surface for a fraction of what government missions typically cost. The entire mission, including spacecraft development, launch, and operations, cost NASA about $118 million through the Commercial Lunar Payload Services program. By comparison, previous robotic lunar missions often cost well over $1 billion each. This wasn't just a cost-saving exercise. It was a fundamental shift in how we approach lunar exploration. Instead of building one-off missions that take decades to develop and fly, once the CLPS program aims to establish a regular cargo delivery service to the moon. Multiple companies compete for contracts, flying frequently enough to drive down costs through economies of scale and rapid iteration of designs. The learning curve has been steep, and not every mission succeeds. Astrobotic's Peregrine lander suffered a propulsion system failure shortly after launch in January 2024, never making it to the lunar surface. These failures are part of the process. Rapid iteration means accepting occasional setbacks in exchange for faster overall progress and lower long-term costs. But success rates are improving as companies gain experience. Japan's Smart lander for investigating Moon Slim demonstrated precision landing technology by touching down within 100 meters of its intended target, proving that future missions can land exactly where scientists want to go, rather than accepting whatever flat, safe area they can find. Even though Slim ended up upside down, its precision navigation worked flawlessly. This capability to land precisely where you want to go changes everything about lunar science and resource utilization. Instead of sending rovers hundreds of kilometers across the surface to reach interesting targets, missions can land directly at the most valuable locations. Polar ice deposits, ancient volcanic vents, suspicious mineral outcrops, and mysterious thermal anomalies all become accessible to direct investigation. The emerging lunar economy operates on completely different principles than traditional space exploration. Government agencies define scientific objectives and purchase delivery services from commercial providers. Companies compete on cost, schedule, and reliability rather than political considerations. Failed missions result in lost revenue rather than congressional hearings, creating powerful incentives for rapid improvement. Multiple nations are participating in this new lunar economy. India's Chandrayaan-3 mission successfully landed near the lunar South Pole in 2023, making India the fourth country to achieve a soft lunar landing. China's Chang'e program continues advancing with sample returns from both the near and far sides of the moon. Japan, South Korea, and several European nations have active lunar programs either flying or in development. This international activity creates a network effect where each successful mission provides infrastructure that benefits all subsequent missions. Communication satellites in lunar orbit provide data relay services for surface operations. Navigation beacons enable precision landing for follow-on missions. Power and communication systems can be shared between different operators, reducing costs and increasing reliability for everyone. The cadence of missions is accelerating rapidly. Where Apollo flew 6 lunar landing missions over 3.5 years, CLPS and international programs plan dozens of missions over the next decade. This frequency enables completely different approaches to lunar science and development. Instead of each mission carrying every instrument needed for complete characterization of a site, missions can focus on specific objectives while relying on previous and future missions to fill in the overall picture. Robotic capabilities are advancing as quickly as launch frequencies. Modern lunar landers carry sophisticated autonomous navigation systems, advanced scientific instruments, and communication systems that provide near real-time data transmission to Earth. Some missions include rovers that can travel kilometers from landing sites, extending the exploration range of each mission far beyond what was possible during Apollo. The business models emerging around lunar services extend far beyond simple transportation. Companies are developing lunar power systems, communication networks, construction equipment, and even entertainment services for future lunar tourists. The moon is becoming a destination where multiple industries can operate profitably rather than just a target for occasional scientific expeditions. Manufacturing capabilities are beginning to appear in mission planning. Several companies are developing systems for producing fuel, water, and construction materials from lunar resources. These in-situ resource utilization technologies could eliminate the need to transport basic consumables from Earth, dramatically reducing the cost of long-duration lunar operations. The regulatory environment is evolving to accommodate this new space economy. The Artemis Accords, signed by more than 20 countries, establish principles for peaceful lunar exploration and resource utilization. These agreements provide legal frameworks for commercial operations while protecting scientific sites and promoting international cooperation. But perhaps the most significant change is cultural. Lunar missions are no longer rare, expensive spectacles that capture global attention for brief moments. They're becoming routine business operations that advance incrementally toward larger goals. This normalization of lunar access makes possible long-term planning and investment that would have been unthinkable when each mission represented a unique national achievement. The shift from government-only to commercial lunar operations mirrors the evolution of Earth orbital spaceflight over the past 2 decades. What began as an exclusively government activity has become a diverse ecosystem of commercial services supporting everything from scientific research to global communications to space tourism. The moon appears to be following the same trajectory, but compressed into a much shorter time frame. This acceleration matters because lunar development enables capabilities needed elsewhere in the solar system. Technologies developed for lunar resource extraction work even better in the asteroid belt. Habitats designed for lunar conditions provide templates for Mars missions. Manufacturing systems proven on the moon could support human expansion throughout the inner solar system. The moon is no longer humanity's final frontier. It's becoming our first industrial outpost beyond Earth. Private companies are building the infrastructure that will support the next phase of human expansion into space, and they're doing it faster and cheaper than anyone thought possible. The question isn't whether we'll establish a permanent human presence on the moon, but how quickly commercial operations can make it economically sustainable. What happens on the moon over the next decade will determine whether human civilization remains forever tied to a single planet or becomes a true spacefaring species. And right now, that future is being built by companies you can invest in using technologies you can understand, following timelines you can track in real time. The cosmic frontier is open for business. Planetary Defense Space Domain Awareness. On September 26, 2022, humanity fired its first shot in a war against the cosmos and won. The double asteroid redirection test spacecraft slammed into the asteroid Dimorphos at 6.14 kilometers per second, changing its orbital period by 33 minutes and proving that we can move worlds when we need to. This wasn't science fiction anymore. This was operational planetary defense using real spacecraft with real navigation systems to solve the ancient problem of rocks falling from the sky. For the first time in Earth's 4.5 billion year history, one of its species had deliberately altered the trajectory of a celestial body, not by accident, not as a side effect, but as a carefully planned demonstration that asteroid deflection actually works. The DART impact created a debris plume visible from Earth-based telescopes, confirming not only that the spacecraft had hit its target, but also that the collision had been far more effective than mission planners had predicted. Instead of changing Dimorphos's orbit by the expected 10 minutes, the impact delivered a 33-minute change, more than 3 times the minimum needed to demonstrate success. But deflection only works if you can see threats coming early enough to do something about them. Most asteroids are darker than charcoal and nearly invisible until they get close enough for their motion against the stellar background to become apparent. Sometimes that's not nearly close enough. This is where the detection gap becomes a matter of planetary security. Ground-based optical telescopes have discovered most of the large civilization-threatening asteroids, but they struggle with smaller objects that could still devastate regions or knock out critical infrastructure. They also have trouble spotting anything approaching from the direction of the sun, since you can't observe what's hidden in solar glare. NASA's Near-Earth Object Surveyor will change this when it launches in 2027. Unlike optical telescopes that hunt for asteroids by their reflected sunlight, NEO, Surveyor will detect their thermal signatures in infrared wavelengths. Every object in the solar system glows with heat proportional to its temperature, and that glow is visible to properly designed instruments, regardless of how dark the object's surface might be or where it appears relative to the sun. The space-based perspective also provides detection advantages impossible from Earth's surface. Atmospheric turbulence doesn't blur observations. Weather never cancels observing runs. And daylight doesn't limit operating hours. NEO Surveyor could potentially operate continuously, scanning the entire sky accessible from its Earth-trailing solar orbit every few weeks. Ground-based detection networks are improving rapidly as well. The Automated Telescope for Asteroid and Tsunami Survey, ATLAS, operates from 4 sites around the globe, scanning the entire accessible sky every 24 hours. It has discovered dozens of small asteroids just hours before they hit Earth's atmosphere, providing real-time confirmation that impacts happen regularly and that our detection capabilities are sensitive enough to spot even small threats. But detection is only the first link in the planetary defense chain. Once you find a threatening asteroid, you need to track it precisely enough to predict its future trajectory, characterize it well enough to plan an effective response, and maintain surveillance capabilities to monitor deflection efforts. This requires a distributed network of sensors and communication systems operating reliably over decades. The Moon plays a crucial role in this emerging defense network. Its gravitational environment provides stable orbits for long-duration observation platforms without the fuel requirements needed to maintain Earth-orbiting satellites. Lunar-based telescopes would have unobstructed views of space without atmospheric interference, while lunar communication relays could provide backup command and control capabilities for deflection missions. Cislunar space, the region between Earth and the Moon, offers unique advantages for planetary defense operations. Spacecraft stationed at the Earth-Moon Lagrange points maintain fixed positions relative to both bodies, providing ideal locations for early warning sensors and deflection mission staging areas. These positions offer gravitational stability with minimal fuel requirements and communication links to both Earth and lunar surface operations. The European Space Agency's Hera mission launching toward the DART impact site will demonstrate how follow-up reconnaissance can refine our understanding of deflection effectiveness. By measuring the exact crater dimensions, debris distribution, and changes to Dimorphos's physical properties, Hera will calibrate models used to plan future deflection missions against different types of targets. This iterative approach test measure refine repeat represents a fundamental shift in how we approach planetary defense. Instead of waiting for a crisis and hoping our theoretical models are correct, we're actively developing and testing the capabilities needed to handle real threats. DART wasn't just a technology demonstration. It was the first operational test of humanity's planetary defense system. International cooperation on planetary defense makes both political and practical sense. Asteroid impacts don't respect national boundaries, so defending against them benefits everyone. Sharing the costs and technical challenges of detection and deflection systems allows more capable defenses at lower cost to each participating nation. The same international frameworks being developed for lunar resource utilization could coordinate planetary defense efforts. Military space agencies are increasingly involved in planetary defense not because asteroids are weapons, but because they require the same kinds of tracking, surveillance, and rapid response capabilities used for national security missions. The distinction between defending against natural space hazards and artificial ones becomes less important when the technical requirements are essentially identical. Current planetary defense capabilities focus on kinetic deflection, changing an asteroid's trajectory by hitting it with a spacecraft because this approach uses proven technology and well-understood physics. But future systems might employ more sophisticated techniques like gravity tractors, solar sails, or even nuclear standoff explosions for the largest threats that require rapid deflection. The timeline for planetary defense operations depends entirely on how much advanced warning we have. Small course corrections applied decades before impact can deflect even large asteroids into safe trajectories. But threats discovered only months before impact might require much more aggressive intervention techniques, assuming intervention is possible at all with such short notice. This is why the detection mission is so critical. Every additional year of warning time makes deflection exponentially easier and more likely to succeed. A comprehensive survey that discovers threats decades in advance transforms planetary defense from a desperate last-minute scramble into routine orbital mechanics. Moving asteroids becomes as predictable as launching satellites. The Moon's role in planetary defense extends beyond hosting sensors and communication systems. Lunar manufacturing could produce deflection spacecraft at costs impossible to achieve with Earth-launched missions. Raw materials from lunar mining operations could supply massive deflection missions without the expense of lifting materials from Earth's gravity well. The Moon could become humanity's first line of defense against cosmic threats. But perhaps most importantly, developing planetary defense capabilities changes our relationship with the cosmos from passive victims to active participants. We're no longer helpless targets waiting for the next impact. We're a spacefaring species with the technology and determination to defend our planet against natural hazards that have been reshaping worlds for billions of years. The Moon has been keeping track of these hazards since the solar system formed, recording every impact in craters that never fade. Now it's our turn to use those records to build the defenses our planet needs. The cosmic shooting gallery is still active, but for the first time in Earth's history, one of its targets is shooting back. The Moon behaves strangely. For more than 1,000 years, people have reported seeing things on the Moon that shouldn't be there. Flashes of light, colored glows, hazes that appear and disappear within hours. Astronomers call them transient lunar phenomena, or TLPs, and they represent one of the most persistent mysteries in observational astronomy. Medieval chroniclers recorded unusual lights near the lunar crater Aristarchus. 18th century astronomers sketched temporary bright spots that appeared and faded over the course of single observing sessions. 20th century observers photographed color changes and glows that defied explanation. And in the 21st century, we're finally beginning to understand what might be causing these ghostly events. The problem with TLP reports has always been separating genuine lunar phenomena from observational artifacts, atmospheric effects, and simple human error. Telescopes vibrate, Earth's atmosphere shimmers, and human vision can be remarkably unreliable when staring at faint objects for hours. Many historical TLP reports probably have mundane explanations, but not all of them. The first hard evidence for actual lunar outgassing came from Apollo-era instruments. Alpha particle spectrometers left on the moon by Apollo 15 and 16 detected radon-222 and polonium-210 emissions from specific locations, particularly around the edges of the Dark Maria and near the Aristarchus crater complex. These radioactive gases can only come from the lunar interior, meaning something beneath the surface was occasionally releasing material into the vacuum of space. Radon detection is significant because radon-222 has a half-life of only 3.8 days. If instruments were detecting it at the lunar surface, it had to have been released from subsurface sources very recently, within days or weeks of measurement. This suggests ongoing geological activity far more subtle than anything visible from Earth, but definitely real and measurable. Modern analysis of historical TLP reports shows clustering around specific lunar locations, particularly the Aristarchus Plateau region. This area contains some of the youngest volcanic features on the moon, along with unusual mineral deposits and thermal signatures that differ from typical lunar terrain. If any region of the moon was still experiencing occasional outgassing or other dynamic processes, Aristarchus would be the most likely candidate. The Lunar Atmosphere and Dust Environment Explorer mission looked specifically for evidence of dust transport and atmosphere dynamics that might explain some TLP observations. LADEE found no visible horizon glow or dust storms of the type that would be apparent to Earth-based observers, placing important constraints on any processes that might loft dust particles high enough to create observable effects. However, LADEE's negative results don't rule out more subtle processes. Electrostatic levitation of dust particles occurs on the moon's surface, particularly near the terminator, the boundary between sunlight and shadow where electrical charging effects are strongest. Individual particles might hop or float briefly in response to changing electrical fields, but these motions are far too subtle to be visible from Earth. Some researchers propose that TLPs might result from impact events too small to create lasting craters, but large enough to produce brief flashes visible from Earth. Meteoroids hit the lunar surface constantly, and occasional impacts by house-sized objects could create momentary glows as kinetic energy converts to heat and light. Several ground-based monitoring programs now watch for these impact flashes, confirming that they do occur regularly. The challenge is distinguishing between genuine lunar phenomena and the countless ways that observational systems can generate false signals. Cosmic ray hits on electronic detectors can mimic brief flashes. Atmospheric turbulence can create apparent color changes in observed objects. Electronic interference can produce spurious signals that seem to originate from lunar locations. But some TLP reports include details that are difficult to explain as instrumental artifacts. Multiple independent observers sometimes report the same phenomena simultaneously from different locations. Some events show spectroscopic signatures consistent with specific gases or materials. Photography occasionally captures features that weren't visible to the naked eye, but show up clearly in long exposures. The most intriguing modern TLP research involves correlating historical reports with current understanding of lunar geology and mineralogy. Areas that have produced the most TLP reports over centuries often correspond to locations with unusual mineral compositions, young geological features, or evidence of past volcanic activity. This correlation suggests that TLP hotspots might represent real geological processes, even if we don't fully understand what those processes are. Recent proposals for future lunar missions include deployment of seismic monitoring networks that could detect small moonquakes or gas releases associated with TLP events. If outgassing does occur sporadically in specific regions, sensitive seismometers might detect the ground motion associated with subsurface gas movement or small rockfalls triggered by thermal expansion and contraction. Gas chromatography instruments on future lunar landers could analyze the composition of any volatiles detected in areas with high TLP activity. Identifying specific compounds released during outgassing events would provide crucial clues about the subsurface processes responsible for these phenomena and their connection to the moon's thermal and geological evolution. The broader significance of TLP research extends beyond lunar science to understanding how apparently inactive worlds can maintain low-level geological activity over billions of years. If the moon is still occasionally releasing gases or experiencing small-scale surface changes, similar processes might occur on other airless bodies throughout the solar system. From a practical standpoint, understanding TLP phenomena matters for future lunar operations. If certain regions experience occasional dust transport gas release or small impact events, These activities could affect sensitive equipment or create hazards for human operations. Characterizing the frequency and intensity of these events helps inform landing site selection and equipment design for long-duration missions. The moon's strange behavior also reminds us that even the most familiar celestial objects retain mysteries after centuries of observation. What appears stable and unchanging from Earth might actually be dynamic in ways too subtle for casual observation, but detectable with sensitive instruments and patient investigation. Perhaps most importantly, TLP research demonstrates that the moon isn't completely dead, it's just very, very quiet. Occasionally, something stirs beneath that gray surface, releasing a breath of ancient gas or shifting a grain of dust in ways that careful observers can detect. These whispers from the lunar interior are messages from a world that still remembers how to move even after billions of years of apparent sleep. The moon keeps its secrets well, but it does keep talking to those who know how to listen. Crater truths. Depth diameter morphology. Every crater on the moon is a fossil of violence, and like any fossil, it tells a specific story about the forces that created it. Learning to read these stories transforms casual lunar observation into active geological investigation, turning every view through a telescope into a lesson in cosmic archaeology. The most fundamental measurement you can make of any crater is the ratio between its depth and diameter. This simple relationship reveals the energy involved in its formation and provides a cosmic ruler for measuring impact forces across the solar system. Small craters maintain what geologists call a simple morphology, smooth bowl shapes with depth to diameter ratios around 1:5. Simple craters form when objects ranging from meters to a few hundred meters across hit the moon at typical cosmic velocities 10 to 20 kilometers per second. The impact excavates a bowl-shaped cavity, hurls debris in all directions, and leaves behind a depression filled with broken rock called breccia. These craters look exactly like what you'd expect from dropping stones into sand scaled up to cosmic proportions. But when larger objects hit the moon, impactors a kilometer or more across, carrying the energy of millions of nuclear weapons, the lunar surface simply can't handle the stress. The initial cavity formed by such impacts is so large and deep that its walls immediately collapse under their own weight, creating the complex crater morphology that dominates large lunar features. Complex craters tell more dramatic stories. Their walls don't maintain the smooth slopes of simple craters. Instead, they collapse into terraced steps that look like enormous amphitheaters carved from solid rock. These terraces form in seconds as unstable crater walls slump inward under lunar gravity, creating the stepped appearance visible in any detailed photograph of large lunar craters. The most spectacular feature of complex craters is their central peaks. Mountains that rise from crater floors like stone fountains frozen at the moment of maximum rebound. These peaks form through a process that seems to defy common sense: solid rock behaving like a liquid under the extreme pressures generated by large impacts. During the formation of a complex crater impact, pressures exceed anything found naturally on Earth's surface. Hundreds of thousands of times, atmospheric pressure temperatures hot enough to vaporize rock and shock waves moving faster than sound through solid material. Under these conditions, rock doesn't just break, it flows like water, following the same rebound dynamics you see when dropping objects into ponds. The central peak represents the maximum rebound of the crater floor solid rock, splashing upward and freezing instantly in its new configuration. In the largest craters, this rebound is so energetic that it creates multiple concentric rings of peaks, producing the multi-ring basin structures visible in places like Mare Orientale, ripples in the solid crust that spread outward from the impact point like waves in stone. These morphological rules provide a universal language for reading impact features throughout the solar system. A simple crater tells you the impactor was relatively small and the target material was competent rock. A complex crater with a prominent central peak indicates a much larger impact involving regional-scale devastation. Multi-ring basins record impacts so massive they sent shockwaves completely around the planetary body, creating disturbances detectable on the opposite hemisphere. The depth-to-diameter ratios of complex craters reveal additional information about impact conditions and target properties. Craters in the lunar highlands tend to be deeper relative to their diameters because they formed in solid rock that maintained structural integrity during excavation. Craters in the Maria, the dark volcanic plains, are often shallower because impactors hit softer basalt flows that were more easily displaced during crater formation. Reading crater floors provides information about post-impact processes and the materials involved in crater formation. Smooth glassy surfaces indicate impact melt rock that was completely liquefied by impact heat and then cooled rapidly in the lunar vacuum. Rough blocky surfaces suggest breccia formation, target rock that was fractured and jumbled by the impact but didn't reach melting temperatures. The presence and characteristics of central peaks offer clues about the subsurface structure excavated by impacts. These peaks contain rock samples from deep beneath the lunar surface brought up by the impact process and now exposed for study. Different mineral compositions in central peaks reveal the layered structure of the lunar crust built up over billions of years of bombardment and volcanism. Crater ray systems provide information about impact timing and the dispersion of ejecta materials. Fresh craters like Tycho display bright rays of pulverized rock extending hundreds of kilometers across the lunar surface. Streams of debris hurled out by the impact and deposited in linear patterns that point directly back to their source. Older craters have lost their ray systems as space weathering gradually darkens the ejected materials to match the surrounding terrain. For practical lunar operations, understanding crater morphology becomes a matter of engineering site selection. Simple crater floors often provide stable, relatively flat surfaces suitable for landing and construction. Complex crater terraces offer natural ramps for accessing crater rims and elevated observation points. Central peaks contain valuable geological samples but may present hazardous terrain for surface operations. The orientation and slope characteristics of crater walls affect solar illumination patterns, thermal environments, and communication line of sight to Earth. South-facing crater walls near the lunar poles receive more consistent sunlight, making them attractive locations for solar power installations. North-facing slopes remain in permanent shadow, potentially preserving volatile materials like water ice. Understanding impact, melt distribution helps identify areas with solid consolidated surfaces versus regions covered in loose debris that might pose mobility challenges for rovers or construction equipment. Knowing the difference between breccia fields and impact melt sheets allows mission planners to select routes and sites appropriate for specific operational requirements. The gravitational signatures of large craters add another layer of information invisible to optical observation. The Gravity Recovery and Interior Laboratory mission revealed mass concentrations or mascons beneath many large impact basins, showing where dense impact melt settled to the bottom of crater floors and cooled into rock more dense than typical crustal materials. These buried mass concentrations create gravitational anomalies that affect spacecraft orbits and provide three-dimensional information about crater structure extending far below the visible surface. Understanding mascon distribution is crucial for precision navigation and long-term orbital stability of lunar satellites and communication systems. Perhaps most remarkably, the mascon patterns preserve the dynamic behavior of rock during the most violent events in planetary formation. These aren't static geological features. They're snapshots of crustal materials in motion, flowing like liquid under the extreme conditions created by cosmic impacts, then freezing in place as permanent records of forces that operate nowhere in terrestrial experience. The Moon's gravity field is a library written in 3 dimensions containing information about impact processes, thermal evolution, and crustal structure that spans the entire history of the solar system. By learning to read these invisible archives, we gain access to stories about planetary formation and evolution that exist nowhere else, preserved in perfect detail by the Moon's gravitational memory. Each mascon is a fossil of violence that continues to affect spacecraft navigation, 4 billion years after the impacts that created it. Proof that cosmic violence, once unleashed, leaves permanent signatures that persist longer than continents, longer than oceans, longer than life itself. Minutes that moved mountains. Recent research has revealed something extraordinary about the Moon's far side: massive valleys that appear to have been carved not over millions of years by patient erosion, but in minutes by cosmic violence operating at speeds that reshape continents faster than you can read this sentence. These aren't the gentle river valleys we know on Earth, carved grain by grain over geological ages by flowing water. These are scars gouged into solid rock by debris flows moving at hypersonic speeds, carrying enough energy to excavate canyons kilometers wide and hundreds of meters deep in less time than it takes to brew coffee. The discovery came from high-resolution imagery provided by the Lunar Reconnaissance Orbiter, which revealed valley systems on the lunar far side with characteristics that don't match any known erosion processes. These valleys are too wide, too straight, and too well preserved to have formed through the slow processes that shape most planetary surfaces. Computer modeling of mega-impact events provides the most plausible explanation for these features. When objects tens of kilometers across hit the moon at cosmic velocities, they don't just excavate craters. They launch curtains of superheated debris that travel hundreds or thousands of kilometers from the impact site, carrying enough momentum to carve channels through solid rock. Think about the physics involved. A 10-kilometer asteroid hitting the moon at 20 kilometers per second delivers more energy than humanity has ever produced in all of history, concentrated into an impact lasting only seconds. This energy doesn't just disappear. It gets converted into heat shock waves and kinetic energy that launches millions of tons of molten rock and vapor in all directions at speeds measured in kilometers per second. This impact ejecta isn't just flying through empty space. It's moving through the lunar environment at velocities that make hurricane winds look gentle. When billion-ton streams of superheated debris encounter topographic obstacles like crater rims or mountain ranges, they don't flow around them like water. They blast through them like cosmic sandblasters, carving channels that follow the most direct path toward their final resting places. The preservation of these features on the moon demonstrates the unique value of airless worlds for understanding extreme geological processes. On Earth, valleys this dramatic would be modified by weather filled by sediments or erased by tectonic activity within a few million years. On the moon, they remain exactly as they formed, providing perfect laboratories for studying the most extreme forces operating in planetary formation. The timescales involved challenge our understanding of how landscapes form. On Earth, we're accustomed to thinking about geological processes in terms of millions or billions of years. Mountain ranges rise slowly as tectonic plates collide. Rivers carve canyons grain by grain over vast spans of time. Even catastrophic events like volcanic eruptions or earthquakes reshape landscapes over periods measured in hours or days, not minutes. But the lunar valleys tell a different story about the pace of geological change. When cosmic violence operates at full intensity, it can accomplish in minutes what terrestrial processes require eons to achieve. The Grand Canyon, carved by the Colorado River over 5 to 6 million years, represents patient work by flowing water. The lunar far side valleys represent instant sculpture by flowing rock, creating similar scale features in time frames shorter than most television commercials. This isn't just academic curiosity about ancient events. It's crucial information for understanding the forces that continue to shape worlds throughout the solar system. Every impact crater we see on planetary surfaces was created by processes operating on these same timescales. The violence that carved lunar valleys in minutes continues to threaten every airless world in the solar system, including asteroids that might someday threaten Earth. The morphology of these rapid formation valleys provides clues about the physical properties of impact ejecta and the mechanics of high-velocity debris flows. Unlike water, which flows around obstacles and follows topographic lows, hypersonic ejecta appears to blast straight through terrain features, creating valleys that ignore local topography in favor of straight-line paths away from impact sites. This behavior suggests that impact ejecta maintains coherent flow characteristics even while traveling at velocities that would instantly vaporize any terrestrial material. The debris streams responsible for lunar valley formation were probably mixtures of liquid rock vapor and solid fragments moving together as integrated flows capable of eroding solid bedrock through sheer kinetic energy. Understanding these processes has practical implications for lunar base planning and safety. If mega impacts can carve valleys hundreds of kilometers from impact sites, they can certainly damage or destroy human installations at similar distances. Knowing the typical range and direction of ejecta flows from large impacts helps identify safer locations for permanent settlements. The research also suggests that some lunar terrain features previously attributed to other processes might actually be impact-related. Linear valleys, unusual crater chains, and anomalous topographic patterns could represent ejecta damage from impacts that occurred billions of years ago, preserved in perfect detail by the moon's airless environment. Dating these valley systems could provide new constraints on the timing of major impact events in the inner solar system. If the valleys formed during the late heavy bombardment, a period of intense impacts around 3.8 to 4.1 billion years ago, they represent direct evidence of the violence that reshaped all inner solar system bodies during that chaotic epoch. But if some valleys prove to be younger, they might record more recent mega impacts that could help calibrate current models of impact risk for Earth and other planets. The lunar surface preserves a complete record of impact history, but we're still learning how to read all the information it contains. The discovery of rapid valley formation also raises intriguing questions about the efficiency of impact excavation and transport processes. How much material can be moved by impact ejecta, and how far can it travel while retaining enough energy to carve channels? These questions have direct relevance to understanding crater formation ejecta blanket distribution and the regional effects of large impacts. For astrogeologists studying other worlds, the lunar valleys provide a template for recognizing similar features elsewhere in the solar system. Mars shows evidence of catastrophic flooding events that carved enormous channels in geologically short timeframes. Some of these features might represent impact-driven processes rather than water-related flooding, suggesting that rapid landscape modification by cosmic violence is a common phenomenon on planetary surfaces. The Moon's role as a natural laboratory for extreme geological processes extends beyond just preserving evidence. It provides a testing ground for understanding forces that operate throughout the cosmos. Every preserved impact feature, every ejecta ray, every valley system carved by hypersonic debris flows teaches us something about the physics of planetary formation and the ongoing evolution of solar system bodies. Perhaps most remarkably, these lunar valleys represent moments when the Moon's surface literally flowed like liquid, reshaping itself in minutes through processes more violent than anything in terrestrial experience. They're snapshots of geological catastrophe frozen in time, preserved for billions of years in the cosmic deep freeze of the lunar vacuum. On Earth, we see the results of geological violence only after millions of years of erosion have softened the sharp edges and filled the deepest scars. On the Moon, we see these events exactly as they happened, with all the raw energy and devastating speed that characterize the solar system's most violent moments. The valleys carved in minutes remind us that the familiar, stable landscapes we know on Earth are actually the exception rather than the rule. Throughout most of the solar system, landscape formation happens not through patient erosion over geological time, but through sudden, catastrophic events that reshape entire regions in moments of cosmic violence. Understanding these processes changes how we think about planetary evolution and the forces that continue to shape worlds throughout the galaxy. The Moon's scarred surface isn't just a record of ancient history, it's a guidebook for recognizing the signatures of cosmic violence wherever they occur, and a reminder that the universe operates on timescales and energy scales that dwarf anything in human experience. Regolith persistence. The Moon is the universe's most patient librarian, preserving every document of cosmic history with obsessive attention to detail. While Earth frantically edits its surface through weather erosion and tectonic recycling, the Moon maintains perfect archives dating back 4 billion years, organized in layers of pulverized rock that scientists call regolith. This isn't soil in any terrestrial sense. It's the accumulated debris of 4.5 billion years of constant bombardment by objects ranging from dust grains to mountain-sized asteroids. Every grain of lunar regolith has been fractured and refractured countless times, creating particles with razor-sharp edges and complex surface textures that trap light in ways that gradually darken the lunar surface over time. The process responsible for this darkening is called space weathering, and it operates through mechanisms impossible on Earth. Micrometeorites constantly pepper the lunar surface, each impact generating temperatures hot enough to vaporize rock and create tiny glass beads enriched with nanophase metallic iron. Solar wind particles, hydrogen and helium ions streaming from the sun bombard exposed surfaces at hundreds of kilometers per second, gradually sputtering away surface materials and implanting foreign atoms into crystal structures. Over millions of years, these processes coat every exposed surface with a patina of impact glass and nanophase iron that absorbs light more efficiently than fresh rock, gradually darkening the lunar surface from its original brightness to the charcoal gray appearance we observe today. This space weathering operates so slowly that it's essentially invisible to human observation, but it's fast enough to erase the bright signatures of fresh impacts within a few million years. The result is a surface that preserves impact features with extraordinary fidelity, while gradually aging them through subtle color changes that reveal their relative chronology. Fresh craters like Tycho shine brilliantly against the surrounding terrain because their excavation processes have exposed unweathered bedrock. Older craters fade into the background as space weathering darkens their ejecta deposits to match the surrounding ancient terrain. This aging process creates a natural timeline readable through careful photometric analysis. By measuring the brightness and color characteristics of different lunar regions, scientists can establish relative ages for surface features without requiring rock samples or complex crater counting statistics. The technique works because space weathering operates at predictable rates under the constant conditions of the lunar environment. But the regolith isn't just a passive record of surface bombardment. It's an active system that continues to evolve through ongoing impact processes. Every micrometeorite impact moves material around, gradually mixing and homogenizing the upper layers while adding new debris to the accumulating deposits. This process, called impact gardening, ensures that the uppermost regolith represents a well-mixed sample of materials from a wide area rather than just local bedrock. The physical properties of lunar regolith pose unique engineering challenges for surface operations. The particles are extremely sharp because there's no wind or water to round off the edges through transport and abrasion. They're also highly abrasive, capable of wearing through metal seals and degrading mechanical systems much faster than terrestrial dust. Most problematically, they acquire electrostatic charges from solar radiation and particle bombardment, making them cling tenaciously to any surface they contact. Apollo astronauts discovered these properties firsthand when lunar dust infiltrated their spacesuits' equipment and sample containers. Despite multiple layers of protection, the dust proved nearly impossible to remove completely, working its way into seals coating optical surfaces and even causing respiratory irritation when small amounts were inadvertently inhaled inside the lunar module. Future lunar missions must account for these regolith characteristics in their equipment design and operational procedures. Spacesuits need better sealing systems and dust-resistant joints. Rovers require protective covers for sensitive components and regular cleaning procedures to maintain operational efficiency. Habitats need sophisticated airlock systems to prevent dust contamination of living areas. But the same properties that make regolith a contamination hazard also make it an invaluable resource for construction and manufacturing. The fine-grained angular particles can be sintered or melted to create glass-like materials stronger than concrete. The mixed composition provides access to virtually every element needed for industrial processes, from oxygen and silicon for life support and electronics to iron and aluminum for structural materials. The persistence of regolith deposits also provides crucial information about the Moon's thermal and geological evolution. Different regions show distinct space weathering signatures that reflect their exposure ages and the composition of underlying bedrock. Highland regions dominated by ancient crustal rocks show different weathering patterns than maria filled with younger basaltic flows. Recent analysis of samples returned by China's Chang'e 5 mission provided the first detailed look at space weathering processes in young lunar materials, confirming theoretical models of how nanophase iron formation affects optical properties. These studies help calibrate remote sensing data and improve our ability to interpret surface compositions from orbital observations. The rheological properties of regolith, how it flows and deforms under stress, become important for understanding crater formation and landscape evolution. During large impacts, regolith behaves like a fluid flowing away from impact sites and settling in topographic lows. This flow behavior affects the final shapes of craters and the distribution of ejecta materials across the lunar surface. Understanding regolith flow also matters for surface operations planning. Heavy equipment can sink into loosely packed regolith, while compacted deposits provide stable foundations for construction projects. Knowing the difference between these conditions helps mission planners select appropriate landing sites and operational techniques. The chemical evolution of space-weathered regolith creates opportunities for resource extraction that don't exist with fresh bedrock. Solar wind implantation has loaded lunar soils with hydrogen and helium-3, potentially valuable resources for future energy applications. Impact glass formation has concentrated certain elements in easily accessible forms that might be simpler to extract than processing fresh rock. The Moon's role as a natural laboratory for understanding space weathering processes extends far beyond lunar science. The same physical and chemical processes operate on asteroids, Mercury, and other airless bodies throughout the solar system. Techniques developed for interpreting lunar space weathering signatures can be applied to understanding the evolution of surfaces we may never sample directly. Perhaps most remarkably, the persistence of regolith deposits means that the moon's surface contains materials from every epoch of solar system history preserved in stratigraphic layers that record changing impact rates, solar evolution, and the chemical composition of the solar nebula from which the planets formed. Each grain of regolith is a microscopic time capsule containing information about conditions that existed when it first crystallized billions of years ago. The moon doesn't just remember what happened to it. It remembers what was happening throughout the entire inner solar system when each layer of regolith was deposited. By learning to read these microscopic archives, we gain access to information about solar system evolution that exists nowhere else, preserved in perfect detail by the moon's patient, obsessive record-keeping. The gray dust that coats everything on the lunar surface isn't just debris. It's a library containing 4.5 billion years of cosmic history waiting for us to develop the techniques needed to read what it's been saving for us. Heavy spots, density interior mascons. Beneath the moon's familiar face lies an invisible architecture of gravity that tells stories no surface feature can reveal. Hidden mass concentrations called mascons create gravitational bullseyes that tug on spacecraft with enough force to alter their orbits, revealing the three-dimensional structure of impact events that reshaped the lunar interior billions of years ago. The discovery of mascons, short for mass concentrations, came as a surprise during early lunar orbital missions. Spacecraft tracking data showed unexpected accelerations as vehicles passed over certain regions, particularly the large impact basins like Mare Imbrium and Mare Orientale. Something beneath these areas was denser than the surrounding crust, creating gravitational anomalies strong enough to affect navigation. The gravity recovery and interior laboratory missions solved this mystery with unprecedented precision. GRAIL consisted of two identical spacecraft flying in formation around the moon, constantly measuring the distance between them with microwave ranging accurate to less than the width of a human hair. As the lead spacecraft encountered gravitational variations, it would speed up or slow down slightly, changing the distance to its companion and revealing the location and intensity of buried mass concentrations. The resulting gravity maps look like topographical charts of an invisible landscape, hills and valleys and gravitational field strength that correspond to density variations hidden beneath the lunar surface. The pattern that emerged was both elegant and unexpected. Large impact basins show distinctive bullseye signatures with dense centers surrounded by rings of lower than normal gravity. This pattern tells the story of what happens when mountain-sized asteroids hit the moon at cosmic velocities. The initial impact excavates enormous volumes of crustal rock, creating cavities hundreds of kilometers across and tens of kilometers deep. But the violence doesn't end with excavation. It triggers a complex sequence of collapse, rebound, and cooling that fundamentally alters the density structure of the lunar crust. The dense centers of mascons represent impact melt rock that was completely liquefied by impact heat and settled to the bottom of crater floors before cooling and solidifying. This melt rock is denser than the original crustal materials because the intense pressures and temperatures of impact remove pore spaces and create new mineral phases that pack more efficiently than typical surface rocks. The surrounding rings of lower gravity reflect the fractured and disrupted crust outside the melt zone. Impact shock waves shatter bedrock for hundreds of kilometers beyond the crater rim, creating networks of cracks and voids that reduce the overall density of affected areas. These damage zones persist for billions of years, creating permanent gravitational signatures of ancient violence. The precision of GRAIL's measurements revealed details about lunar interior structure that had been impossible to determine from surface observations alone. The data shows that the lunar crust varies dramatically in thickness from less than 30 kilometers on the near side to more than 60 kilometers in some far side highland regions. This asymmetry might reflect the moon's early thermal evolution or the effects of Earth's tidal forces during crustal formation. More intriguingly, the gravity maps reveal linear features and geometric patterns that suggest the lunar interior is far more fractured and complex than previously imagined. The crust appears to be shot through with ancient fracture systems, possibly related to tidal stresses when the moon was much closer to Earth, or to the global scale disruption caused by the largest impact events. For spacecraft navigation, understanding mascon locations and intensities is crucial for mission planning and orbital mechanics. The gravitational variations are strong enough to significantly perturb satellite orbits, requiring constant course corrections to maintain stable trajectories. But they also enable new types of missions frozen orbits that take advantage of mascon effects to maintain stable paths with minimal fuel consumption. The mascon signatures also provide a new tool for exploring lunar subsurface structure without drilling or seismic surveys. By correlating gravity anomalies with surface geology and impact crater distributions, scientists can map the three-dimensional architecture of the lunar crust and identify locations where subsurface resources might be concentrated. Some mascon regions show evidence of more complex structures than simple impact melt pools. Multi-ring gravity patterns suggest that the largest impacts created nested systems of dense deposits, possibly reflecting multiple episodes of melting and solidification during prolonged crater formation sequences. These complex signatures provide clues about impact dynamics and cooling rates that help calibrate models of crater formation throughout the solar system. The discovery of mascons also revolutionized our understanding of lunar thermal evolution. The formation of dense impact melt deposits requires enormous amounts of heat input over relatively short time periods. The distribution and characteristics of mascons provide constraints on the thermal state of the lunar interior during the period of heavy bombardment when most large basins formed. Ground-penetrating radar data from orbital missions combined with gravity measurements begins to reveal the internal structure of some mascons in 3 dimensions. These combined datasets show that impact melt deposits can extend to depths of several kilometers, representing truly massive volumes of rock that were completely liquefied and then slowly cooled over thousands of years. The preservation of mascon signatures for billions of years demonstrates the geological stability of the lunar interior. Unlike Earth, where plate tectonics and mantle convection constantly rework crustal structure, the Moon's interior has remained essentially unchanged since the major impact basins formed. This stability makes the lunar gravity field a perfect laboratory for studying impact processes and their long-term consequences. For future lunar resource utilization, mascon locations might indicate concentrations of useful materials. Impact melt rocks often contain metal deposits concentrated during cooling, while the fractured zones surrounding mascons might provide access to subsurface volatiles or unusual mineral assemblages created by shock metamorphism. The Moon's hidden gravitational architecture also provides training for understanding similar processes on other worlds. Every large impact throughout the solar system creates similar patterns of excavation, melting, and structural disruption. Techniques developed for interpreting lunar mascons can be applied to gravity measurements of Mars, Mercury, and large asteroids, helping us understand the impact history and internal structure of worlds we may never sample directly. Perhaps most remarkably, the mascon patterns preserve the dynamic behavior of rock during the most violent events in planetary formation. These aren't static geological features. They're snapshots of crustal materials in motion flowing like liquid under the extreme conditions created by cosmic impacts, then freezing in place as permanent records of forces that operate nowhere in terrestrial experience. The Moon's gravity field is a library written in 3 dimensions containing information about impact processes, thermal evolution, and crustal structure that spans the entire history of the solar system. By learning to read these invisible archives, we gain access to stories about planetary formation and evolution that exist nowhere else, preserved in perfect detail by the Moon's gravitational memory. Each mascon is a fossil of violence that continues to affect spacecraft navigation 4 billion years after the impacts that created it. Proof that cosmic violence, once unleashed, leaves permanent signatures that persist longer than continents, longer than oceans, longer than life itself. Fork in the road, lunar arc, or lucky roll. We stand at a decision point that will define the next chapter of human civilization. For the first time in our species' history, we possess both the technological capability to establish a permanent residence beyond Earth and the scientific knowledge to understand why we might need to. The Moon offers us a choice: become a spacefaring civilization with multiple worlds to call home, or continue rolling the cosmic dice with everything we've built, concentrated on a single planet. The path forward requires parallel strategies that reinforce each other, defending Earth while diversifying beyond it. This isn't about choosing between planetary protection and space expansion. It's about recognizing that the same resources and technologies needed for effective planetary defense also enable a permanent human presence throughout the inner solar system. The immediate roadmap begins with a comprehensive reconnaissance of lunar resources and habitability. We need detailed mapping of polar ice deposits to understand their extent, purity, and accessibility. Current estimates suggest billions of tons of water ice in permanently shadowed craters, but we lack the precise measurements needed for industrial planning. Robotic missions over the next decade must provide ground truth data on ice distribution depth and extraction feasibility. Simultaneously, systematic exploration of lunar lava tubes and pit sites will identify the most promising locations for permanent habitation. The stable temperatures and natural radiation shielding offered by these features make them ideal sites for humanity's first permanent settlements beyond Earth. But we need detailed structural surveys to ensure their safety and habitability. In situ resource utilization demonstrations represent the critical path for lunar industrialization. We must prove that we can reliably extract oxygen from lunar regolith, purify water from polar ice deposits, and manufacture construction materials from local resources. These technologies determine whether lunar settlements can become self-sustaining or remain dependent on expensive supply lines from Earth. The first permanent lunar installations should be small protected nodes that demonstrate closed-loop life support systems while providing platforms for expanded operations. Picture a facility built into a natural lava tube or protected by regolith berms capable of supporting a dozen people year-round while serving as a test bed for larger installations. This facility would validate human factor requirements, test equipment reliability, and refine operational procedures for permanent off-world living. Parallel development of planetary defense capabilities requires completing the detection infrastructure needed to provide decades of warning for threatening asteroids. The Near-Earth Object Surveyor telescope launching in 2027 will dramatically improve our ability to spot dark asteroids approaching from any direction, including the solar glare regions invisible to ground-based telescopes. Ground-based detection networks like Atlas already demonstrate the feasibility of continuous sky monitoring, but they need expansion and redundancy to ensure comprehensive coverage. The goal is a detection system robust enough to spot city-killer asteroids decades before potential impacts, providing time for careful deflection planning rather than desperate last-minute interventions. The Moon's role in planetary defense extends beyond hosting observation platforms. Lunar manufacturing could produce deflection spacecraft at costs impossible with Earth-launched missions. Raw materials from lunar mining operations could supply massive deflection missions without the expense of lifting materials from Earth's gravity well. Most importantly, lunar industrial infrastructure could provide the surge capacity needed to respond to multiple simultaneous threats or unexpectedly large objects requiring heavy lift deflection systems. This dual-use approach infrastructure that supports both human settlement and planetary defense makes economic sense in ways that single-purpose systems cannot. Every dollar invested in lunar resource extraction contributes to both settlement sustainability and deflection mission capability. Every advance in lunar manufacturing supports both habitat construction and spacecraft production. The timeline for this development spans multiple decades, but begins with decisions made in the next few years. Current lunar missions must transition from scientific exploration to resource characterization and technology demonstration. Private companies developing lunar delivery capabilities need sustained support and clear regulatory frameworks to justify long-term investments. International cooperation remains essential for both technical and political reasons. No single nation possesses all the capabilities needed for comprehensive lunar development and planetary defense. Sharing costs, risks, and benefits among multiple partners increases the likelihood of sustained commitment through changing political circumstances. The Artemis Accords provide a framework for this cooperation, but implementation requires ongoing diplomatic and technical coordination. The human factors of permanent off-world living present challenges as complex as the technical ones. How do people maintain physical and psychological health during multi-year assignments in low-gravity and enclosed environments? How do lunar communities maintain cultural connections to Earth while developing their own local identities? These questions require careful study and gradual development of solutions through increasingly long-duration missions. Environmental protection of the lunar environment must be considered from the beginning of large-scale development. The Moon's airless environment means that dust and contamination spread far from their sources, potentially interfering with astronomical observations or scientific sites. Responsible development requires zoning systems that separate industrial activities from environmentally sensitive areas while preserving access to the most valuable resource deposits. The economic model for lunar development must evolve from government-funded exploration to commercially sustainable operations. This transition requires identifying products and services that lunar installations can provide more efficiently than Earth-based alternatives. Satellite servicing, asteroid mining support, and Mars mission logistics represent potential revenue streams that could sustain lunar operations beyond their scientific and defense missions. Perhaps most importantly, we must recognize that developing lunar capabilities changes humanity's fundamental relationship with cosmic risks. Instead of being passive targets, hoping that dangerous asteroids will miss us, we become active participants in solar system dynamics with the industrial capacity to deflect threats and the backup habitats needed to survive catastrophic impacts. The choice isn't between staying on Earth or abandoning it for the Moon. The choice is between remaining a single-planet species vulnerable to cosmic accidents or becoming a multi-world civilization capable of protecting our home planet while expanding our presence throughout the solar system. The Moon has been keeping records of cosmic violence for 4.5 billion years, documenting the ongoing reality of impact threats while preserving everything we need to build defenses against them. Now it's our turn to use those records wisely, building the future that our cosmic neighborhood's violent history tells us we need. Time moves differently in space than it does in politics. Asteroids don't adjust their trajectories for election cycles or budget negotiations. The cosmic processes that created the Moon's crater record continue operating on timescales that dwarf human planning cycles, but demand human responses measured in decades, not centuries. We have the knowledge, the technology, and the opportunity to build humanity's insurance policy against cosmic catastrophe while establishing our species' first permanent foothold in the larger universe. The question isn't whether we can do this. It's whether we will choose to do it before we need it, rather than after we need it. The Moon waits patiently as it has for billions of years, keeping perfect records and offering everything we need to protect ourselves. The choice is ours, but the clock is cosmic, and cosmic clocks don't stop ticking for human convenience.